Starting from version 2.2.24 of the Walls of Steel, the sextant has been completely fixed, and we can get the correct values for the altitude of celestial bodies as well as their correct time readings when measuring the altitude. We have a Nautical Almanac which now includes data on the Sun and 58 navigational stars. To make celestial navigation closer to reality, I will teach you how to use Kriegsmarine F-Tafel tables for calculations, and you will be able to calculate altitude and azimuth in the same way as a U-boat navigator. You can download the necessary documents from the link in the video description and print them on paper, as I did. F-Tafel are used together with a special form in which calculations are carried out. Before we start working with F-Tafel, I will explain what these tables are and how they work. Many formulas are required to explain this, but you don't need to memorize these formulas. F-Tafel tables are so simple that you can use them without knowing any formula. However, I admit that the things I'm talking about may not be too obvious and may not be clear the first time. But even if you find it difficult to understand the theoretical issues, do not be afraid to move on to the practical part of this video. You will definitely succeed. You can always return to the theoretical part of the video later if you need it for a deeper understanding. In training videos 2.1 and 2.2, methods for determining the latitude at the moment when the star is located on the meridian of the observer were considered. Determination of latitude was carried out in two arithmetic operations, since we considered three angles, declination, latitude and zenith distance, which lie in the same plane. Simple arithmetic works here because 3 points, the celestial pole, the zenith and the star, lie on the same line, which is meridian of the observer. If the star is not on the meridian of the observer, then the celestial pole, zenith and the star form a triangle on the surface of the celestial sphere. This is a spherical triangle, and in order to find the zenith distance it is necessary to solve this triangle using spherical geometry. F-Tafel embodies a fairly simple way to solve spherical triangles. The celestial pole that corresponds to the observer's latitude is used as the vertex of the spherical triangle. This is the upper celestial pole. When explaining the F-Tafel, I will use the German transcription of designations and symbols. According to F-Tafel, the vertices of a spherical triangle have the following designations. Zenith is designated by the German letter Z. The upper pole is designated as PO. The vertex corresponding to the celestial body is denoted by the German letter G. Each side of a spherical triangle is an arc that corresponds to an angle with a vertex in the center of the celestial sphere. 90 degrees minus the latitude of the observer, 90 degrees minus the star declination. The third side is the zenith distance, 90 degrees minus the altitude. The sides of a spherical triangle form spherical angles between themselves on the surface of the celestial sphere. The spherical angle, the vertex of which is at the zenith of the observer, corresponds to the azimuth of the star. The spherical angle, the vertex of which is at the celestial pole, corresponds to the local hour angle, which is denoted by T. The law of cosines is used to solve spherical triangles. In order to find the cosine of one side, it is necessary to multiply the cosines of the other two sides and add the product of the sines of these sides, multiplied by the cosine of the spherical angle between them. Altitude and zenith distance are complements to each other, because the sum of these angles is 90 degrees. The cosine of an angle is equal to the sine of its complement. You can simplify this expression by replacing the angles with their complements. We replace the zenith distance with the altitude. Replace the complement of latitude with latitude. Replace the complement of declination with declination. The local hour angle remains in place. Pay attention to the second part of the equation. If T is 90 degrees, then the second part of the equation becomes 0, because the cosine of 90 degrees is 0. To simplify the calculations, F-Tafel uses a trick that allows you to use this reduced formula. If we put aside a spherical segment B from the zenith, which forms a right angle with the opposite side, then the spherical triangle will be divided into two right-angled spherical triangles, ZLPO and ZLG. We can apply the reduced formula to solve the triangle ZLG, where the opposite spherical angle for the zenith distance is the right angle instead of the angle T. So, to calculate the altitude using the ZLG triangle, instead of the latitude complement, we will use the spherical B segment. Express the side of GL, which we will use instead the declination complement. This spherical distance is called U in F-Tafel terminology. The GL side is the declination complement reduced by U. The formula for solving the ZLG triangle is as follows. Note that the cosine of B is used instead of the sine of latitude, because unlike latitude, B is the side of a spherical triangle but not its complement. For calculations, we need to use two auxiliary parameters, U and B, which depend on the local hour angle of the star and on your latitude. To make it convenient to perform calculations using this formula, it is necessary to transform it in such a way that multiplication is replaced by addition. For this, the property of logarithms is used. I'll give you a simple example that will make everything clear to you. See how the same mathematical operation is represented here in three ways. Let's imagine that you know absolutely nothing about logarithms and you have the task of multiplying 100 by 1000. You probably just add 2 and 3, not knowing that in this way you applied the property of logarithms. Calculations using F-Tafel are carried out just using this property of logarithms. Instead of multiplying two numbers, we will add their logarithms. To write this formula in a logarithmic way, not the value B itself is used, but the logarithm of its cosine, which is denoted as phi. Replacing the factors in the formula with their logarithms, we replaced multiplication by addition. The result is exactly the formula that is implemented in F-Tafel for calculating the altitude of celestial bodies. If you skip the details, which I will definitely tell you later, Then the calculation of the altitude using F-Tafel is done as follows. First, you need to calculate the local hour angle of the celestial body. Then, based on your local hour angle value and your assumed latitude, you extract the U and V values from the table. Calculate the sum of U and the declination of the star. Using the result obtained, extract the logarithm of its sign from the table. Calculate the sum of V and the logarithm of the sign that you extracted from the table. The result will be the logarithm of the sign of the altitude, and you can extract the altitude from the table using this value. Even if at the moment you do not understand how it works, don't be worried about it. In any case, I propose to immediately begin practical training to work with F-Tafel. If you are able to add two numbers without using a calculator, then you are definitely able to master F-Tafel. In my opinion, at least 90% of success in mastering F-Tafel lies in studying this form for calculations, also known as side reduction table. Once you understand the structure of this form, you will understand how to use F-Tafel. This form is essentially a short guide to working with F-Tafel, and each step of the calculations on this form is accompanied with by notes containing the numbers of the tables that must be used and the values that must be used to enter these tables. These fields are used to write down initial information, dead reckoning position, celestial body name and observed altitude, date and time of altitude measurements. These fields calculate the local hour angle in degrees, which should be converted to hours, minutes and seconds, according to the ratio where 180 degrees corresponds to 12 hours. This is the route by which the altitude is calculated according to the formula that we already know. The line of position transfer is calculated in this column, and on the right side of the form the azimuth is calculated. Before starting the calculations, it is necessary to enter the dead reckoning position, the name of the celestial body, the observed altitude, the date and time of the altitude measurement into the form. The full degree closest to the reckoning latitude must also be entered. Important note: line of the position transfer calculation will be carried out relative to the full degree of latitude that you specified here. This is because F-Tafel contains U and V values only for full degrees of latitude. Line of position transfer will be carried out on the map relative to the point with these coordinates. The height of the observer's eyes above the sea surface should also be entered. A little later I will tell you why you need to take into account the height of the eyes. The height of the eyes must be calculated using the formula. This formula is suitable for those conditions when the observer is on the bridge of the 7th type of U-boat. U-boat depth is the depth of the U-boat keel. The top edge of the conning tower outer railing is located about 9.5 meters above the U-boat keel. 10 meters in this formula is the height of the observer's eyes relative to the U-boat keel. Subtracting the U-boat depth from 10 meters gives the height of the observer's eyes above the sea surface. When the U-boat is on the surface, its depth is 5 meters, and the height of the observer's eyes in this case is 5 meters. Now about what the height of the observer's eyes affects. Until now, when we talked about the horizon, we had in mind the astronomical horizon, the plane of which forms a right angle with the plumb line. Until now, we have not assumed that the apparent horizon is different from the astronomical horizon. In fact, the eyes of the observer are not on the surface of the sea. The apparent boundary between the sky and the sea is tangential to the surface of the Earth. The apparent horizon seems to be fallen relative to the astronomical horizon. There is a difference between the altitude relative to the astronomical horizon and the altitude relative to the apparent horizon. This difference is called dip of the horizon, or simply dip. Dip and atmospheric refraction values are included in the Gesamtbeschickung, a total correction that must be applied to the observed altitude. As you know, the zenith distance is the side of a spherical triangle. The zenith distance corresponds to the angle the vertex of which is in the center of the Earth, and therefore is a complement to the geocentric altitude relative to the astronomical horizon. For this reason, the solution to the spherical triangle should be based on the geocentric altitude relative to the astronomical horizon, which must be obtained by applying the total correction Gesamtbeschickung to the observed altitude. F-Tafel contains separate tables for determining the total correction of stars and for the Sun. Table F7 serves to determine the total correction of the altitude of the stars, which is the sum of dip and refraction. The total correction for stars is always negative, since both dip and refraction overestimate the altitude. For a total correction of the Sun's altitude, table F8 is used. In addition to dip and refraction, the total correction of the Sun's altitude includes the value of the Sun's semi-diameter. If you measure the altitude of the lower edge of the solar disk, then the correction for the Sun's semi-diameter is positive, and the total correction for the Sun's altitude can be positive when the Sun's semi-diameter value exceeds the sum of the absolute values of dip and refraction. An example of determining the total correction for the altitude of the Sun using the F8 table was shown in video 3.3. The initial data for determining the total correction are the observed altitude and the eye height. The total correction value that you extracted from the table must be applied to the observed altitude. We calculate the local hour angle of the celestial body. How the local hour angle is calculated is shown in detail in video 3.1. The steps in calculating the local hour angle of a star are to calculate the Greenwich hour angle of the first point of Aries and the Greenwich hour angle of the star at the time of measurement. The reckoning longitude must be added to the Greenwich hour angle of the star. When performing the addition, the longitude sign must be taken into account. East longitude is positive, west longitude is negative. The calculated value for the local hour angle must be between 0 and 360 degrees. The angle T is in a spherical triangle cannot be more than 180 degrees, and if the calculated value of the local hour angle exceeds 180 degrees, in fact you are operating with an angle that is measured from the local meridian in the east direction. F-Tafel uses the concept of west and east local hour angle, which are counted in hours, minutes and seconds in the range from 0 to 12 hours, in the west and east directions respectively. Thus, every 15 degrees of the local hour angle corresponds to the T angle of exactly 1 hour. The local hour angle is a kind of key that F-Tafel opens. Everything we have done so far has been just preparation. To find the correct key to F-Tafel, use the F0 table, which is included in Silent Hunter 5 Nautical Almanac. To do this, you need to answer two questions. The first question is, what is the closest full degree of the calculated value of the local hour angle? In our example, this is 65 degrees. Using the value of the full degree, it is necessary to extract from the table the corresponding value of the local hour angle TA in hours and minutes, a multiple of 4 minutes. 4 hours and 20 minutes in our case. Next, you need to determine the difference in arc minutes between the calculated value of the local hour angle and its closest full degree, 8.7 degrees in our example. On the right side of the table, take the delta T value in seconds of time, which corresponds to the difference in arc minutes, 35 seconds in our case. This value can be either positive or negative. Now, in order to correctly determine the sign, it is necessary to answer the second question. How many seconds of time must be added to the calculated value of the local hour angle to get TA? When answering this question, you need to focus on the values of the local hour angle in hours and minutes of time. So you need to reason like this. The calculated local hour angle is an hour angle of 4 hours and 20 minutes, reduced by 35 seconds. This means that 35 seconds must be added to the calculated local hour angle to get 4 hours and 20 minutes exactly. Thus, delta T has a value of plus 35 seconds. You need to be especially careful here. I will give an example that will show how you can make a mistake when determining the sign. Imagine that the calculated local hour angle is 294 degrees and 51.3 arc minutes. The closest full degree is 295. This will correspond to the same 4 hours and 20 minutes as in our example. Up to a full 295 degrees is also missing 8.7 arc minutes, which corresponds to 35 seconds of time. You may mistakenly believe that you need to add these 35 seconds of time to the calculated local hour angle, as this should bring you to the nearest whole degree. In fact, your calculated local hour angle is 35 seconds greater than 4 hours and 20 minutes. You need to subtract these 35 seconds to get exactly 4 hours and 20 minutes. So, delta T sign in this case will be negative. After calculating and converting the local hour angle, we make notes that the local hour angle is less than 6 hours and belongs to the first quarter of a circle. This is important for calculating the altitude and azimuth. I will talk about this later. Using the local hour angle TA and the declination of a celestial body, it is necessary to extract from F-Tafel an auxiliary value P, which is used to determine the azimuth of a celestial body. The hint contains the numbers of two tables, F1 and F11, as well as the values that are used to enter this table and extract P. Local hour angle and declination. First, the F1 table is used. Find the section in the table that corresponds to the local hour angle TA. Using either of the two outermost columns, find the row in the table that corresponds to the absolute value of the declination of the celestial body. In our case, the declination is between 19 and 20 degrees. P is between 31 degrees and 31.6 degrees. We take P to be 31.3 degrees. Pay attention to the dotted line that is in the F1 table. If you extracted P above the dotted line, as in our case, then you do not need to use the F11 table. You simply take into account the value that you got from the F1 table. In other cases, if you see that you need to extract P below the dotted line, then the F1 table is not accurate enough for this, and you should use the F11 table, which takes into account the angular minutes of the declination, for a more accurate calculation of P. In table F11, from the column that corresponds to the local hour angle, take P, which corresponds to the full degree of the declination of the celestial body, 31 degrees and 2 arc minutes. Next to P is the increment of P for each declination arc minute between 19 and 20 degrees of declination, 0.58 arc minutes. You need to calculate the P increment for 25 arc minutes declination using the exchange table on the last page of F-Tafel. Add the resultant increment to P for 19 degrees of declination and write the result as decimal degrees. As you can see, we get the same P value as in the F1 table. Using the local hour angle and full degree of the latitude, we proceed to calculate the altitude. According to the formula we know, we determine the altitude value, which corresponds to the local hour angle of 4 hours and 20 minutes exactly. To get the final result, it is necessary to make a correction to the calculated altitude based on the fact that we have determined the altitude for the local hour angle, which is greater than the calculated local hour angle by 35 seconds of time. The calculation of the altitude begins with entering the F1 table with the value of the local hour angle and latitude in order to extract from the table the auxiliary values U and V necessary for calculating the altitude, as well as the third auxiliary value for determining the azimuth, which we will talk about later. To calculate the sum of the declination and the U value, it is necessary to determine the sign of the U value. The angle T in the general case can be acute or obtuse. When T is an acute angle, then the spherical segment B lies within the spherical triangle. When T is an obtuse angle, the spherical segment B lies outside the spherical triangle. In the case of an acute angle T, in order to find the altitude, the declination complement must be decreased by U. In the case of an obtuse angle T, in order to find the altitude, the declination complement must be increased by U. It can be seen from the formula that the value U is derived from the latitude of the observer. The factor that determines the sign of U is the cosine of the angle T. In the case of an acute angle T, the cosine of T is positive, so the value of U has the same sign as the observer's latitude. This is indicated in the hint. U has the same sign as the latitude if the local hour angle belongs to the first or fourth quarter of the circle. The word gleichnamig in German means has the same sign. In the case of an obtuse angle T, the cosine of the angle T is negative, so the value of U has a sign opposite to the observer's latitude. This is also indicated in the hint. U has a sign opposite to latitude if the local hour angle belongs to the second or third quarter of the circle. The German word ungleichnamig is used for the opposite sign. It is necessary to perform the algebraic addition of the declination and the value U, that is taken into account the signs. Regardless of whether the result obtained after the addition is positive or negative, we will use its absolute value. Sign is no longer taken into account. It is necessary to extract from the table F2 the logarithm of the sign for the result obtained. Due to the periodicity of trigonometric functions, the same column in the table F2 is used for two angles that add up to an angle of 180 degrees. For angles that are listed at the top of the table, the leftmost column with angular minutes is used. For angles from the bottom of the table, use the rightmost column of angular minutes. You need to keep this in mind in order to avoid mistakes when you work with the table. On the right are exchange tables for calculations with tenths of arc minutes. From the column for 35 degrees, we write out two values between which the angle we are looking for is located. The first value corresponds to 54 arc minutes. The second value corresponds to 55 arc minutes. To find the exchange table for tenths of arc minutes, you need to find the difference between these two values. We need exchange table with the number 18 in the header. This is a column with tenths of arc minutes. This is the column with the corresponding increment of the logarithm. 2/10 of an arc minute corresponds to a 3.6 logarithm increment. The increment is rounded to the nearest number, 4. Add 4 to the logarithm of 54 arc minutes and write down the result. The result obtained must be added to the φ value to obtain the logarithm of the sign of the altitude. Before adding these two numbers, you need to keep in mind that in fact they are not literally logarithms. The fact is that the sign takes values from 0 to 1. The logarithm of 1 is 0 and the logarithm of values from 0 to 1 is negative. For the convenience of calculations, in the F2 table, 10 was added to the logarithms to get a positive number. That is, the mathematical record of the table values looks like this. If we add these two numbers, then we get the result in this form. Since we need to extract the altitude from this result, we need to bring it to the form that corresponds to the table value. We always need to subtract 10 after addition. It looks like we are adding only those numbers that are after the comma, and the nines before the comma are not of interest to us. We are actually discarding 10 from our result. In order to extract the altitude from the table, we need to do the opposite of what we did. We write out two values between which our result is. We see that the exact value of arc minutes is between 3 and 4 arc minutes. In the way we already know, we find the exchange table for calculating tenths of arc minutes. We need exchange table with the number 21 in the header. The difference between the logarithm of 3 arc minutes and the logarithm of the calculated altitude is 18, and this is more consistent with 9/10 of an arc minute. We write down the altitude. Before we calculate the altitude correction for the 35-second difference of the local hour angle, we need to calculate the azimuth since it participates in the calculation formula. The azimuth is determined by selecting a suitable value in the F1 table or in the F11 table using the value P and the measured altitude. We start looking for the azimuth in the F1 table. Focusing on the line that corresponds to the measured altitude, you need to find the column with the azimuth in which the value P will be closest to the calculated P value. If the line that corresponds to the measured altitude passes below the dotted line in the column with the found azimuth, then the F11 table should be used. You already know the principle of working with the F11 table, only this time you need to enter this table not with the declination but with the measured altitude. Find the column with the azimuth that you determined from the F1 table and calculate the value P for that azimuth, as well as for two adjacent values using the measured altitude value in degrees and minutes of arc. From the three values, choose the one that is closest to the previously calculated P value. Write down the azimuth that corresponds to the selected P value. The azimuth that we extract from the tables is a value from 0 to 90 degrees, and we need to determine one of 4 possible ways to plot this azimuth on a circle. To do this, we need to consider another element of the celestial sphere which we did not talk about. We know that the observer's meridian passes through the zenith and the north and south cardinal points. The circle of the celestial sphere that passes through the zenith and through the east and west cardinal points is called the prime vertical. Let's make a projection of the celestial sphere in such a way that the meridian of the observer and the prime vertical are segments that divide the horizon into 4 parts. Here we will depict the equatorial system of celestial coordinates. In a horizontal coordinate system, the observer's meridian, and the prime vertical form 4 quarters, which are called quadrants. Having determined the azimuth value from the tables, it is necessary to determine in which quadrant the azimuth is located. In the equatorial coordinate system, the observer's meridian and the celestial meridian corresponding to the local hour angle equal to 6 hours divide the celestial sphere into 4 parts. To determine the quadrant, the first thing to do is to determine on which side of the meridian of the observer the celestial body is located. This is very easy to do if you know which local hour angle a celestial body has, east or west, since the meridian of the observer is a common element for the horizontal and equatorial systems. The east azimuth corresponds to the east local hour angle and the west azimuth corresponds to the western local hour angle. Knowing the position of the celestial body relative to the meridian of the observer, in order to determine the quadrant, you just have to determine the position of the celestial body relative to the prime vertical. And there are two options here. The azimuth can be measured from the cardinal point, which corresponds to the lower celestial pole, or from the cardinal point, which corresponds to the upper celestial pole. You need to check two attributes by which you can immediately determine from which pole the azimuth is measured. If the local hour angle is more than 6 hours, then the azimuth is measured from the upper pole. If the declination has a sign opposite to the latitude, then the azimuth is measured from the lower pole. If none of the conditions are met, then the celestial body is in this region of the celestial sphere, and we need an addition criterion to determine which side of the prime vertical the celestial body is located on. This criterion is the Grens declination. Literally, Grens declination is the boundary or limiting value of the declination at which a celestial body having a given local hour angle at a given latitude is on the prime vertical. Grens declination is an arc passing from the celestial equator to the prime vertical along the celestial meridian on which the celestial body is located. By comparing the absolute value of the declination and the Grens declination, you can determine from which pole the azimuth of the celestial body is measured. If the declination is greater than the Grens declination, then the azimuth is measured from the upper pole. If the declination is less than Grens declination, then the azimuth is measured from the lower pole. In our example, the upper pole is the North Pole. The local hour angle is west, so our calculated azimuth is west. The local hour angle of the celestial body in our example is less than 6 hours, and the declination has the same sign as the latitude, so it is impossible to immediately determine the azimuth quadrant. The declination of a celestial body is less than a Grens declination. Now we can determine the azimuth quadrant. Using the azimuth value, latitude, and the addition to the local hour angle in seconds of time, we use the table to extract the correction to the calculated altitude in minutes of arc. The table contains a 0.25 factor for converting seconds of delta t to minutes of arc. Interpolation must be performed to obtain an accurate value. The correction sign corresponds to the delta t sign. Before line of position transfer calculation, we present the azimuth in the usual form, in which it has a value from 0 to 360 degrees and is counted in the western direction. The found azimuth is measured from the southern cardinal point, which corresponds to 180 degrees in the western direction, which is considered positive when reading the azimuth. To save time, Messkarte can also be used to quickly find azimuth. The error in finding azimuth with Messkarte usually does not exceed 1 degree, and this will not lead to critical errors in determining the U-boat position if you are away from the coast and if you are doing that reckoning carefully. The azimuth from Messkarte needs to be converted to be between 0 and 90 degrees, so that you can determine the altitude correction with the F-Tafel. Subtract the calculated altitude from the measured altitude and calculate the transfer of the position line. The transfer in angular minutes must be multiplied by 2 to calculate the transfer in kilometers. A positive transfer is carried out in the direction of the calculated azimuth. A negative transfer is made in the opposite direction to the calculated azimuth. An error of 2 or 3/10 of arc minutes in determining line of position transfer is quite acceptable. If you have never worked with calculation tables, then in order to start mastering F-Tafel, first of all I recommend that you do the same calculations yourself with the same initial information as I did. Then just compare your calculations and mine. In the next step, I recommend that you start the Baltic operation and carry out astronomical observations on your own in similar conditions. That is, also observing the Arcturus as about the same time and in about the same place. Make your own line of position transfer calculations using F-Tafel. Check your calculations with the Excel spreadsheet. In the future, until you have assurance when working with F-Tafel, let the Excel spreadsheet be your insurance.